Okay, I'll kick up the live stream, but then I'll need a few more minutes before we get started. All right, let's try it like that. And I miss the other room with the adjustable desk very much. Yeah, if anyone's joining on the live stream, let me know if things don't work. There was a warning from YouTube once again, but maybe it's fine. As always, as on Friday, we're waiting for a few more from the tutorials that that others might attend. But if you have some questions, we can discuss that. Thanks for checking, Walid. Live stream seems okay. Perfect. Yep, that's the right unit, but of course we already started. Go over that. So let me also remind people that I promised you to show you a hint for this puzzle. So we'll do that at the end so that everyone's here. If there are questions about the formalization, now is a good time to cover that. Yeah, there's a question on Slido. No, we won't be starting with the puzzle. We'll finish with the puzzle. I think that's the better order. That gives the people who come from the tutorial late the chance to start on that from the beginning. The motivating story behind it is one thing, but you can basically read the formalization in isolation. Maybe in preparation for later. Let me draw that here. Okay, if I smuggle that in between, this will be a bit confusing, but I'll figure it out. So I'll encode and decode. So for anyone who arrived late, I'm just preparing something for later. We'll get started in a minute. It's not 28 past, right? No. Okay. Should look at that clock. I'm just preparing this. We'll do this at the end of today's slot. But I want to write it up already so I don't waste the time later. I call that B. So that's the discrepancy, but actually the mark we could write as 20 minus n minus. Okay. What I've done so far is just copied what is on the website. The only thing I replaced the numbers 20 and 10 by letters. That's all. As I said, we'll come back to that. Are there questions at this point? Yeah, we will cover the puzzle later, not now. Yeah, the tutorials are not recorded for various reasons. I don't think we'll have the power to change that. But you get all sorts of material from them. Hopefully that's enough. In case someone needs the attendance code, let's show that again. And if you could put in your got it, so I roughly get the count for how long to wait later. It's always amazing how little 80 people looks in this big room. Unless there actually aren't 80 people in the room. Okay. Ready, steady, go. I found it a bit dim in here. I don't know, the light's really low. Let me run back and switch it a little brighter. I can hardly read my notes. It's a little better. I think you can still see the screen. Good. All ready? Everyone awake? As much as possible. Right. In the next subsection, we'll look at some lower bounds for what you can possibly achieve with codes. And the goal was to have codes that can detect or correct errors, or maybe both, right? I motivated last time a bit why communication, even for a computer where things are stored in binary, has noise sometimes. And just as a reminder, we'll look at specifically the type of noise where one bit can be flipped or twisted from its actual value to the negation. We won't look so much at other types of errors, although they are potentially also relevant. But in the situation where you transmit some signal over a wire, where the timing is somewhat given, and just the value that you receive is disturbed, that's the right model to look at. So we'll focus on that. And we'll start with, as always, lower bounds are proofs about what's possible. So you have to say, what are all possible things? So we'll start with formalizing this a bit. So our model will be as follows. We start with the source message S. That's an arbitrary bit stream. So remember, this is just a string over that alphabet of arbitrary length. And we have some communication channel, which will basically just mean that whenever we send something, any bit could be flipped. So instead of S directly, we will send the encoded version of S. Hopefully, I'm adding enough redundancy to correct these flips. So instead, we'll actually send C, so another string. That's the same notation as in the compression unit, but remember, the goal is the opposite. We're not trying to reduce storage space. We're trying to add redundancy in. And then there's two functions. We need to encode and to decode. Encoding happens at the sender, decoding happens at the receiver, and hopefully they get the same answer. All right. That model is overall a bit too generic to make any interesting statements. So instead here, we'll focus our attention to block codes. And all that means is that instead of sending the entire string here of arbitrary length, we only look at m bits at a time. That's a block. So we'll send k bit blocks over from the source text. But what we'll send will have more bits, namely n, and that's what comes out of the encoder. So I'll just write this as C of m here. So C is the output, the coded text, and the function that produces that. I hope it's clear from the context in each time whether it's the output or the function that computes it. Now, of course, the way you use this is, as you would obviously expect, you take the first k bits of your source message, encode that in the first n bits, send those, then you go to the next block. And the receiver inverts that in the obvious way. It takes n bits that they receive, then they decode that to k bits, and then they go on to the next n bits that are received. This works perfectly if you never ever lose bits. If there would be a channel that inserts or deletes bits, then you might miss what the block boundaries are, and then you have to work around problems there. Because we don't look at that, a block code is essentially general. There's nothing lost by looking at things blockwise. If I send a block of n bits, anything between 0 and n bits might be flipped. In an actual scenario, of course, we would assume that it's not so likely that all the bits get flipped. But we won't get into the probabilities here. All that we show is essentially worst case results. And we'll make guarantees what the codes can do. And if there's more things flipped than they can handle, then we won't receive the original message. And so again, the two things we try to do is detect and correct. And the question for a block code then will be, how many bits can we flip to tolerate so that we can still detect there is a some error happening? And how many can we flip so that we can still correct to the original message without retransmitting? Okay. There's one key property of codes that only becomes possible by looking at these block codes, but that will be very useful. That's the notion of code distance. So here's the first simple observation. If I have an encoding that takes two different source messages and maps them to the same coded text, the same coded block, that can never work, because it's impossible for the decoder to, even without errors, to know which was the source message. So the encoding function is always injective. It produces different outputs for different inputs. And that means we can't have an arbitrary number of those. So let me be more specific. If we define the set of code words curly C as all the code words you obtain, so this is the set of all n-bit strings. So it's the set of all blocks, so that there exists a message in the of k bits, which produces this block. Then we call that a code word. So it's all bit strings that you can obtain from a message when you encode it without any bit flips. Now, because of this injective property, it means for every message I have a different code word. So I have at least as many code words as I have messages, and I only have so many because I can't have more. There's no others coming around. So the size of the set of code words will always be the same. It's always 2 to the k, because that's the number of different messages I can send. But the code words themselves are n bits long. So I have 2 to the k n-bit words, or n-bit strings, and these are my code words. Now, if I define a coding function like this, I can do a generic decoding, which is in a way always best possible like that, where I say I just decode it to the closest valid code word. We'll see examples of this later. If you fix this decoding, which is, I think, a natural thing to do, because it makes the assumptions that more errors are less likely. So you always decode to the thing that would have resulted in this with the fewest number of bit flips. Then you can define the distance of a code as the minimal distance of any two code words. And here's this notion Hamming distance. That's just the number of positions where these words differ. So in particular, if I had, just to practice that a little, I have a fun example. Let's do a boring example. What's the Hamming distance of those two strings? Should have prepared a Slido question. Well, we can just look at which letters are the same. So A is the same, and the last A is the same. But then these two are swapped. But for the Hamming code, all that matters is that this is different and this is different. So it's Hamming distance 2, right? It's two positions where the letters are not the same. Hamming distance is only defined if the two strings are the same length. So we never have to worry about what happens if one string is shorter. That's not a thing. So if I take the Hamming distance of all the code words, all pairwise distances, that's what this minimum is doing. It picks any two code words. I guess any two code words that are not the same. Otherwise, we get a 0. Then that minimal Hamming distance, that's called the code distance. So far, that's just a definition. And I hope the next few slides convince you that it's a reasonable definition. And the first property that follows from this comes straight away. When I want to detect up to d-1 bits of an error, so if I want to be able to correctly detect that something went wrong for up to d-1 bits flipped, then I need code distance d. And the reason for that is simple. If there were any two code words, I'll draw them like this. I mean, they live in some high-dimensional discrete space, but I'll just draw them in the plane as an intuition. So it's done. This is not exactly to scale in any sense, but okay, and that's not the middle. Okay, sorry. For that picture, I should just put that here. So what should these dots mean? That's one code word. And that's another code word. And the distance between them here, if that is d, then I can definitely not detect errors where d bits have been flipped, not correctly detect. Because there's a way to get from x to y by flipping d bits. That's what the code distance says. The Hamming distance between x and y is d. So if I started with x, I had a message that produced x as code word. Now my channel flips d bits. Then I arrive at the code word I would have gotten for message y. And it looks exactly like the code word for message y. There's no way for me to know that I actually started with x and had these d bit flips and distinguish that from the situation where I started with code word y. So there's two possible explanations for receiving y. One is we send a message so that exactly gives you y as a code word. It is a code word. So if x and y are in this curly C, y is a code word, so there is some message that gives you that. Or other possible alternative universe, m was sent. The block for that is x, the code word, and d bits flipped. That's the proof why if you want to detect d-1 bit errors, you need distance d. You cannot detect d errors, d bits flipped with this code of distance d. At least there's one input where it doesn't work. That's the first part. The second is a little more interesting because that gets closer to error correcting, what the point of the whole unit is. And it says a similar statement. If you want a certain number of bits to be able to be corrected, you need a certain minimal distance. And the reason for that, let me draw a similar picture. And we will again have these two situations, A and B. So we send a message and then flip d minus 1. Oh, let me give that another name, flip t bits. So one option is I started with x and then I somehow went to x prime, which lies in a radius of size d, t. So imagine these balls are Hamming distance circles, which are more like weird squares or cubes, but it's nicer to draw it like that. And then the other situation is we have a code word y, running out of space here. Second situation is we started from another message, and then we flip to t other bits. But we end up at the same thing that is sent over the wire. So we in both cases end up with x prime. That would mean that x prime also lies in a circle around y of Hamming radius dt. Okay. So that means for sure here the Hamming distance of x and y directly is at most 2t, right? Because I can get from x to y by flipping first t bits and then more t bits. Maybe some of these flips are at the same positions, then the distance is actually smaller, but at most it's 2 times t. If you invert that statement, you get the claim here. So this shows you if the code has distance 2t or less. There's an instance where you can start from 2 legit messages, you get the code words, and you flip t bits each, and you collide on the same thing. So if a receiver receives x prime, there's no way for them to know whether it was whether it was m or m prime that was originally sent, because both have a way by flipping t bits to arrive at the same bit pattern. Okay? So if you want to be able to correct t bits, you need to have at least 2t plus 1 as a distance for the code. Otherwise, no chance. And if you invert that and write it nicely, that's the second line. So you need distance d to have d minus 1 half bits, and then you can say that's your t. Now, important remark, the way these things are formulated, they are correct, but they're only implications in the one direction. They say, if you want a certain number of errors to be correctable, your code definitely needs distance at least so and so. But it doesn't tell you that any code with that distance guarantees that you can correct errors. That's not necessarily the same thing. Okay? So as they're written, there are just implications in the one direction. But we're in the section on lower bounds, so we'll make statements like this in this case only. Based on this observation, there's 2 lower bounds that tell you something about specific codes. And I want to show you these very briefly, just because I think they're useful to keep in mind, and they're useful thinking patterns. So in this case, we fix the block length, and we'll fix the message length, and we fix the code distance. 3 parameters flying around. And then we'll have certain statements that mean these parameters have to relate in a certain way. Okay, let's see the first example, the singleton bound. It's by a person called Singleton, not that it's necessarily no other meaning of the word. It's just the name. The way it's easy to show is this inequality. But because it's 2 to the k, 2 to the n minus d minus 1, you can just take logs on both sides. And then you get this, you can rearrange to this nicer statement, which is more intuitive. if you have these three parameters given, usually the message length and the code distance is what you want to fix, and then you want to know how big do my encoded messages have to be? How much redundancy do I have to add? And this bound tells you, okay, if you want a message length k and a distance d, you at least have to add those up and subtract 1. That's your minimum code length for sure. You definitely can't do better. It doesn't promise you that this is doable, and it usually isn't. Well, let's briefly prove why this is true, this first part. Remember what I said before about the code words? Every message gives you a different code word, injective encoding. So we can write down all those code words below each other. And again, I'll just sketch this here schematically, not for any specific set of parameters. That keeps going. So these are your 2 to the k code words. And they each have n bits, right? Now we know more. We know that they have distance d. So whenever I pick 2 of these code words, I know there's at least d positions where they differ. Same notation as in the string matching chapter. The little bold is just there's a difference there between the characters. So if we now take the first d+1 bits, so in all of those, we chop off the first d-1 bits, and we now only look at the code words that remain after that line, okay? Because I only removed d-1 bits, and every pair of code words differed by at least d positions, there will be one difference to the right of the bar. The worst case would be if they all lie here, but then there's at least one more on the right, just not enough left. That's all that this proof says. It's a very simple proof. So if all of these 2 to the k strings are different afterwards, then we must have that the lengths relate like this, because there's on this side, the strings that remain are n minus d minus 1 long, right? In parentheses, the subtraction. And there's 2 to that length many different bit strings with that many bits. And we've just shown that they're all different, so there must be enough of these more than 2 to the k. Okay, that's the proof of the singleton bound. That's all there is. And it gives you this nice statement about how these 3 parameters relate. And it's particularly nice because it tells you straight away, give me k and d, and I'll compute you a lower bound for the block length. It's often not tight. Often you can't achieve that bound. You can't find a code that gives you straightly this. So there's a second bound, which is often a bit more powerful. And indeed, we'll see instances where we match exactly that bound. So in a way, that bound is best possible, or strictest possible. That's the Hamming bound. And this is more complicated. I can't easily give you a formula that, given k and d, tells you how big n has to be. It still has the same flavor. N is bigger than something. You can rearrange this, right? It's the same as saying 2 to the n is at least 2 to the k, and then times this lovely sum. Let me use this abbreviation t again. It's defined below here anyways. And I'll remind people that these are binomial coefficients. You should know what these are. Otherwise, ask Wikipedia afterwards. So this is also an inequality of these parameters, and it in a way tells you that n should be bigger than this, but it's a little less explicit. Why is that true? That uses, again, the picture from before. if we have our balls around a certain code word, then we know that the code has distance d. So if I go from here to there, I need to flip at least d bits. Right? And if you look at how t is chosen, it's the same as before. It's half of that distance, but rounded down if it's odd. And okay, I subtract 1 and then round it down. So I always make it strictly smaller than half. So the radius of these balls can be t, but they don't touch. The balls are disjoint. Okay? That's step 1. Maybe I should put the whole thing in quotes. The quotes are just because it's not really round. But you can still imagine the set of all bit strings that have Hamming distance at most t. So that's what we'll do here. We count all the bits that have Hamming distance at most t from a given code word. And how many are there? Well, if you do this more seriously than in this graphical representation. Okay, I don't know if I can draw this properly. Let me stick with that image. There's a few that are just around x at distance 1. These are flipping 1 bit. Okay, and I can pick any position in x. So any of the n positions I can flip. So that gives you the size of this set of things at most distance t from x is 1 for x itself, plus n for all the strings that I get from flipping 1 bit, plus n choose 2 for choosing any 2 positions to flip 2 bits, and so on. So I sum those up. F is the number of flip bits, and I can flip at most t. And these are all disjoint sets, so I can all sum them up. So we count these. That's the ball size, and that's this sum. Okay. Now, every code word gives you one ball of that size, namely code words. We know the balls are all disjoint. So every code word gives you a full ball of code word of bit strings that are taken. We know all the balls are disjoint. So if I sum up all the ball sizes, number of balls times how big they are, I cannot use any bit string twice. So that product has to be at most 2 to the n. And that's precisely what's written here. So that's a more delicate bound, but it's much more tight to what is actually doable to achieve a code with a small distance. Okay. Let me put up the question we discussed yesterday already. So if you voted yesterday, no need to change your votes. I asked you 2 questions. One was this one. If you want to send 100 bits and you want to be able to detect a single bit error, how many extra bits do you have to add to the 100 bits? And then I also asked the second question for the same thing with correcting instead of detecting. Oh, come on. It's very slow. So that was the word cloud for the second part. If you want to Why is this still saying detect? This one. Okay, that's what I wanted to do yesterday. Let me just fix this by changing the text here. Goodie. I think I said it clearly yesterday, but didn't look at Slido for the right thing. Again, if you voted yesterday, no need to change. In the next section, we'll answer those two questions, and so you can check how your guess related to those. I should probably lock them now. So, goodie. Okay, everything clean again. So we can keep going. In the next section, we will look at upper bounds for these codes, concrete constructions that give you certain error detecting and error correcting codes. And we'll, of course, hold them against the definitive lower bounds we've just seen, which are impossibility results. They show we cannot do better than certain things. So we know what to aim for now. But let's get there step by step. The first simple trick that most of these codes are based on, I think all the codes I know are in a way based on it, is this simple trick. It's the parity bit. And you can formulate it two ways. We add one extra bit. And in this bit, we put, well, one bit of information, either 0 or 1, depending on whether all the other bits overall have an odd or an even number of 1s. Now, there's two ways to explain this. Either is you take the XOR of all the bits, and that's the extra bit you send. The other option to define it is the whole thing with the parity bit added has to be an even number of 1s, irrespective of what the message was. And so in that sense, the parity bit makes sure that everything is in pairs or is even. Pick whatever you find more intuitive. If you look at that from the block code angle, it gives you a code of distance 2. Because there's always if you flip one bit, you definitely destroy the parity. Right? If you started with an even number of 1s, no matter whether you flip a 1 to a 0 or a 0 to a 1, you'll end up with an odd number of 1s afterwards. And that's not a valid code word. So in our code here, not on the slides. Let me add it. Valid code words are those with even number of 1s. Right? And every other code word is like that. So you always have to flip at least 2 bits to get from one to the next. And that means the code distance is 2. And amazingly, they can detect single bit errors because if you flip a single bit, it makes the parity odd, and you can detect that by just summing up the number of 1s. Now it can do more. Any odd number of flips has, of course, the same effect. But if you flip an even number of bits, it goes unnoticed. Now this is so fundamental that many pieces of hardware use this as a sanity check in between. It's not, without getting into further details, I mean, this is often used as a sanity check, and what you do if you detect an error is a different question, depends on the application. That's not our focus here. It's very, very simple and cheap. You can do this XOR operation easily in hardware. That's why it's often used at this lowest level. But of course, it has a code distance 2. So what does that mean from our lower bound section? Well, if anything, it can only detect 1-bit errors, and it does. And it can potentially correct how many bits flipped? Well, 2 minus 1 divided by 2, rounded down, so that's 0. You can correct 0-bit flips. Amazing. So it cannot correct any errors. It can only detect things. So we've had that question, and I just want to show your votes in from previously for the recording. But also, I guess you now have a different answer. I locked this one, so you can't change it. But I have the question again. So if you want, you can put your new answer in. But I won't wait for you on this one. So that was cute. The error detection we kind of handled in one slide. Error correction is a bit more interesting. And I want to motivate why this is a really useful thing. So a typical, a real-world application for error correcting codes is computer main memory. Now, simple cheap devices, or well, cheap, but most of your laptops and mine won't have this. Because the assumption is your laptop doesn't run for months and months in one go. So if there is an occasional rare event of a flip in your memory, you'll just reboot and it'll be fine. Now, if you want to dig into this a bit deeper, some person wrote a very lovely blog post where they did some nerdy Unix tricks to figure out what happened. There was a program crashing, and they nailed it down to a 1-bit difference between the copy of that program in main memory and the program on disk. And so it's kind of clear there that what must have happened is that the bit in memory has been flipped by something. And indeed, sunstorms and cosmic rays can do this. Remember, these are super small nanoscale charges, and it doesn't take so much to flip them. We're close to the quantum world, so things are not as deterministic as our abstraction treats them like. And so these are very real. And if you have a heavy-duty server with lots of bits in its main memory running for months on and on, it's actually a reasonable chance that one of the bits will be flipped at some point. It's very unlikely that you will see 2 bits flipped, but one is a real thing. Right, so that's why heavy-duty server RAM has an error-correcting code built in to recover from that gracefully without rebooting and so on. Now, that said, how would we possibly do this? And we'll focus very much on this kind of motivation where 2 bits flipped at the same time and close to each other is super unlikely. That would mean really winning the lottery twice in a row. But winning the lottery once, if you buy millions of tickets, remember main memory is big, is actually billions, not millions, maybe more, is occasionally happening. Okay, so how could we possibly do this? There's actually a very simple solution. Maybe you thought about this. I don't know. You can just store everything 3 times. If one of the copies is corrupted, you have 2 other copies. So whenever you're asked to decode a bit in memory, you just take the majority vote of 3 bits, and that's your answer. That corrects any 1-bit error, right? And again, if you have more than 1 bit flipped, let's suppose that's so unlikely that we don't care. Now that's great. So actually, error correcting codes aren't so hard. The only slight downside is that it triples the cost. You can only use 1/3 of your main memory. And that costs money and it costs energy. Maintaining the integrity of your main memory is one energy-hungry part in keeping computers running. I mean, on a laptop, it's often the screen that eats most, and then the CPU is often, if it's doing something, is a lot of the energy. But if the CPU is idling, then main memory might be the next biggest energy consumption. And so we don't want to triple the main memory, right? That's just that would be too much. And what I'll show you in this cute little section does the same thing with 11% of redundancy. So instead of tripling the cost, we multiply the cost by 1.1. That sounds more modest, so 1.11. That sounds reasonable. Paying 10% extra for recovering from occasional sunstorms seems a reasonable price. And that's why this price is paid where it matters. Again, I locked the question, but let me show what you thought back then for correcting things. Unfortunately, Slido doesn't do a good job of averaging this. That was the question where I was telling you yesterday, tell me how many bits you need to correct a 1-bit error. Although the Slido question said detect. So hopefully not too much confusion arose. And well, at least some person said 11, that's great. And we got all sorts of numbers, bigger and smaller. What you could have figured out yesterday from first principles is that 200 bits should be enough, right? This tripling, sending everything 3 times, that definitely works. So we never need something crazy like this. But of course, then otherwise, it was probably just guessing that you could do. So let's see how this works. All right. Amazingly, we'll use parity bits again, but we need several of them so that we can narrow down what happened more. And the core idea will be we take parity bits not of the whole message. There's no use in doing that several times over. Instead, we'll use well-chosen subsets of the bits in the message and cover them with one parity check. And from the combination of these parity bits, you can conclude things. All right. Now, okay, you have to be prepared that also the parity bits can be flipped. So you have to make sure that it works in that case too. Here's a concrete setup that we'll focus on where the message has 7 bits. That's the block size that we sent. Sorry, not the message. The block size has 7 bits. And the 3 colors show the subsets that we use for parity checks. It will always be 4 positions. The blue one takes the first 4. Then the green one takes the first 2 and these 2. And this one takes every other starting with the first. And the way we define them, as for parity checks before, we set, we define that summing up all those in XOR should get 0. So we should have an even number of 1s in the 4 blue, the 4 green, and the 4 magenta bits. Okay, that's a definition for now. So every valid code word, right? So a 7-bit string is a code word if and only if it satisfies these 4 constraints, 3 constraints. Some simple observations. If we send these 7 bits and nothing happens, then all of these are 0, right? And then I can treat these 3 bits as one number, as a binary number, and it comes out as 0. Now, let's suppose that there's 1 bit flipped. So I sent these 7 bits, and 1 bit gets twisted. Any preferences? Which one shall we flip? Shout a number. 5? I mean, either works. Let's take that one. If that one gets flipped, it will affect the blue and the magenta one, right? Yeah, can't write. So blue is flipped and magenta is flipped. So if I decode this string C, I get 1, 0, 1. If I read that in binary, that's a 5. Oh, cool. That's the thing that we flipped. And I mean, I made it sound like that's a surprise, but it was constructed like this. If you think about how these are selected, the blue exactly select the 4 ones. That's those where the first bit in the binary representation of the index has a 1. The second is the one where the second bit of the binary representation has a 1. These are these two. And the last bit is easy to see because it alternates. All the odd indices have the magenta thing included. That's 1, 3, 5, 7. Okay. So what this means is if we get such a 7-bit string, and it originally had this constraint satisfied, and we flip 1 bit, then this checking code C tells us exactly what bit was flipped. But that's amazing because then we can undo the flip. Right? It's just one position that we flip back, and then we know what the original 7-bit string was. And because this works for every of the 7 positions, these are all possibilities covered. The 8th possibility is that no bit is flipped, which we can also detect. Then C is already 0. So that's a cute definition of code words. It's not a code yet, right? So I haven't told you how to take a source message and encode it using this code. But we're actually not far away from that. To turn this into a code, and this is called Hamming code. It's a specific instance of a Hamming code. We'll come back to that, but I think it's if you understand this one, you'll understand the concept. So that's again just copied from the last slide. This definition of checking bits. Now, if you pay close attention, there's some of these bits that occur in only one constraint. This one, and this one. It happens to be those at indices powers of 2. So instead of saying we have this constraint and they have to be 0, we can set those 3 bits so that the constraint is satisfied. Because they're independent, they're always just included in one of the constraints, I can independently make every constraint satisfied. And so that's what we do for the Hamming code. For the encoding step, we're given 4 bits. That's our message length. And we'll put some color. Let's do these in green. So I put these at these positions. That's the first step. Then I compute the parity bits for each of these positions so that that is satisfied, which just means for the blue one, I take the parity of these, XOR those 3 together. If that's a 1, then I put a 1 at this point, otherwise a 0. So that's indicated here with these lines. I think the picture looks wilder than the construction actually is. So you do this for all the 3. Then the checking bit string is 0. Then you can send that. And the decoding we basically already covered. You determine this C. And if that's not 0, you know 1 bit where you have to flip. And then you just pick these 4 positions and ignore the parity bits. That's the decoding. So spelled out, if we receive a block of 7 bits, we compute C 2 slides back. If that is 0, we're happy. Otherwise, we flip exactly that 1 bit that is determined by C. And we have to pick out the right positions to return. Let's see if you digested this. I might need a minute to think through. And I'll go back to that slide. I think that has all the information on it somewhere that you need to answer it. We had 80-ish people earlier, or did it go up further than that actually? Wow, 114. Let's at least wait for 80, roughly. I don't have a question otherwise that I asked only today. Well, there's a clear majority for the right answer. So let's just briefly unpack why that's true. Maybe on this slide is cleanest. The thing is, you have to make C back to 0 before you find another code word. And for that, you have to flip 3 bits, because it's not actually obvious to prove, maybe. But because you can correct 1-bit errors, you kind of could work backwards that you need at least 3. And you can also say there are code words of distance 3, because I can flip these 3 bits. But most of these are, I can flip 3 bits and get back to another code word. Yeah, I guess that's the worst case. So you flip 1 bit, you have to correct 2 other counting bits. It's actually a bit tricky to prove. Let's not prove it on the spot. But 3 is the code distance of this Hamming code. Now let's compare this with our lower bounds from before. We had the Hamming bound earlier, and there we said we related these as follows. So I had 2 to the n has to be greater or equal 2 to the k, and then you sum up the number of flip bits from 0 up to d minus 1/2 rounded down, and then n choose f. So what do we have to put here? The length of the blocks is 7. The number of the bits in the source thing is 4. And the distance is 3, as we just convinced ourselves. So if you work this out in this example, you get exactly 2 to the 7. And that means you have exactly as many code words as code words are in the size, in all the balls summed up. So there's nothing actually left. You're using every 7-bit string in radius 3, Hamming radius 3 distance ball around all your code words. So you exactly cover the space of 7-bit strings with your balls. That's the tight case. It often doesn't work out like this if you have other parameters. But here it does. And we can correct 1-bit errors, as we've seen. If you're thinking about doing more with the same code, we could potentially detect at least 2-bit errors, right? 3-bit errors are out of the question with a distance 3, but maybe we can detect 2-bit errors. Now, if 2 bits are flipped, we will know that something has been flipped. But what actually happens is that our decoder happily decodes it to another source message, thinking that it is a 1-bit error. Because of this tightness, it means whenever you start at a code word and you flip 3 bits, you must end up with another code word because the whole space is covered. Or at least you must be in the ball of one other code word. So if you do two bits, sorry, so situation is like this. The distance between those is at most 3. So if you flip 2, you enter the ball of another code word. And so instead of going from here 2 bits, you will correct it towards that one. So we can't really see whether 2 bits were flipped. We would mistake it as a different 1-bit error. There's a variation that people often use where you add an 8th bit, which is just the parity of the overall block that you send. And that allows you to detect 2-bit errors as well, but you can't correct them. So it's kind of it's a bit of a hack on top of the Hamming code. But it can be useful to at least detect these very much more unlikely 2-bit errors, but at least know that something went wrong. Okay. Now I said this 7,4 Hamming code is one specific instance of a general recipe. Actually, the code of just tripling a single bit is the trivial version of a Hamming code. And in general, you can do the same thing. Maybe let me just motivate this from the picture here. We took the positions of powers of 2 and used those for parity bits. That's what happened here. And you can do this in general. That's what that slide says. The overall number of bits in your block is 1 less than a power of 2. Because we need to be able to encode every position with the checking bits plus the 0 case where no bit was flipped. Then we can use the L bits at indices at a power of 2 as the parity bits, and the rest we can send as data bits. So that's the general recipe. Ours corresponds to L equals 3, and L equals 2 is just the triple everything. And you can make L bigger. That's how I came up with these 11%. If you set L to 7, you can correct any 1-bit error in 120 bits. And a standard computer memory word would be 64-bit. So if you want to protect that, you need this 11% overhead, even though you're not actually using all the data bits you have. So overall, Hamming codes are still very simple enough to encode, to implement them in hardware. And they massively reduce this overhead from just tripling everything. That's why they're fairly widely used. A brief comment on what is not so easily possible. So the generalized Hamming codes that we've seen are called perfect codes because they exactly match the Hamming lower bound. So we have a matching lower bound. We can't possibly do better, and we have an upper bound that achieves it. So everything great. So we cannot possibly do better if, well, the message length has a specific form that comes from the construction, and we want to do specifically correct 1-bit errors. If you go away from any of these two assumptions, it's not clear. Hamming codes might not be the best possible choice, and we might not even know a code if you want to correct more errors. And for many of the parameter choices, the search is basically still open. It's still an open research question to find best possible error-correcting codes. There's a fun fact that I won't get into. Is an old proven result. You may know Claude Shannon as the founding father of information theory. He proved this basically in his first treatise of the topic. If you in a certain way choose your code words randomly, so the code words in the space of 2 to the n-bit strings, if you choose those randomly with a little bit of a cleanup, you usually get a good code in the sense of good distance. But if you pick arbitrary code words, there's no clean encoding procedure that gives you a way to get from your message to that code word and back in a fast way. So in a way, we know there's reasonably good codes close to the respective lower bounds, but they're useless because they're too slow and they're hard to find. And so people are still looking at tricks for specific parameter choices to do better than that. That's all I wanted to say about error correcting codes. As you know, as you've seen now, it's basically these two lower bounds and the Hamming codes. But I think it's a nice excursion. It shows some other cute constructions. Now let me see if there. But if you have questions on this unit, we should cover those first because now it's fresh. Okay. Some stray votes. So far, I only see one question about what is information theory. It's the field of study of that stuff and other things. So it studies what's the intrinsic information content of a string. We've covered that question in the compression part, about the Kolmogorov complexity and these things. It also covers codes that do error correction or how to transmit the information over a noisy channel in the best possible way. These two things are covered in information theory. Oh, and now I misread the question. What is information entropy? Okay, cool. I told you what information theory is, in case anyone wanted to know. Entropy, I mean, we defined the simple version of entropy in the compression unit. Are parity bits the only way to detect errors? Feels, I mean, probably not, right? I'm sure you can come up with other ideas. It's the main idea that is used over and over because it's so simple and it works well with bits. And you can generalize it, as we've seen in the Hamming codes, to take a subset, and that seems to be good enough. There's variations. There's these cyclic redundancy checks. So you can go from treating things as individual bits to numbers. But in a way, that's still a parity check in disguise, if you want. I know, you want to hear the hint on the assessment, on the programming puzzle. So let's go back to that. So here's again the formalization. And let me find my diligently prepared little write-up. There we are. My hint is basically on the slide, plus one more thing I'll say. What I did on this, as I said earlier, is just introduce parameters for the two main quantities in the formulation. There's a number of questions that you have to answer, and there's a number of bits that you're allowed to send or transmit via these honking or this story. If you go away from 20 and 10, you can make other instances of the problem. If you're presented with a problem that seems unclear or tricky, like in this case, the obvious mental block that most people first have is, how can you possibly do better than 10? And I mean, what can you do with 10 bits? You can arbitrarily say, I'll give you the answers for the first 10 questions. And I mean, you should be at least scoring 10 then. But can you do better? It feels like all you can do with 10 bits is send 10 bits of information, right? And that part is true. Now, my hint is, if you take these parameters Take the same problem, but make the parameters smaller. It's a general recipe. If you're given an algorithmic problem and you have no idea how to solve it, you try to solve manually the small cases first. And sometimes you learn something from it. Sometimes you don't because you went too far. Sometimes you made the problem trivial, boring, by making the parameters too small. Well, if that happens, you make them a little bigger until the problem starts to bite again. Maybe I'll leave it with that for now, but I can give you concrete parameters a bit later. But I guess it's more fun if you start playing from this. So what's the smallest possible instance? I guess if you set k to 0, you can do nothing at all. That's clearly boring. You can only guess. So you could say the number of bits you can send is just 1. And then the number of questions you can also reduce. If you set the number of questions to 1, that's probably boring. So you want to start with something slightly bigger. Yeah, okay, now I already... So if you choose 2 questions, that's still kind of degenerate. So you want to go just above that. The good thing about so small instances is there's not so many possible instances. You can just write them all down and figure out for each of them what would be a good strategy to attack it. I'll promise if you do that, it'll probably click and you'll see ways to generalize it. I also want to give away that the puzzle has the same feature as the previous one, that I don't know the actual final answer. There's a part of it, part of it is open. I mean, I know a small range where the answer has to lie, but I don't know the final answer. So you can surprise me. Yeah, maybe you have a great idea that, yeah, that solves that one. That's all I want to say on this for now. Maybe you're disappointed. I don't know. But give it a go. Spend at least half an hour thinking on the small cases. Then you should... that's the usual time it takes for a good drug to work, right? If you take some aspirin, it also takes 20 minutes, half an hour. Yeah. I guess we should take a break, and we started a bit late, so we could do a few more minutes on the next section. Let me check if it makes sense. If we stop in the middle of the thing, maybe it's not worth it. Well, let's take a break for now for sure. And that way I can skip the fire alarm. Maybe. Yeah, I'd like to define the problem when you come back. So let's do 5 to 10 more minutes on the next unit, just covering the first few bits. Easygoing stuff. Ooh. All right, slowly time to continue. I've seen I spent a lot of time when I taught that section last time, so I'm not sure if I'll give all the detail I did back then. Or we'll have to split it in half. So once more, welcome back to Efficient Algorithms COMP526. We'll look at a new unit, branching out a bit from the previous topics. This time we'll look at parallel algorithms. It's a little detour into this world of speeding up algorithms further by using multiple cores or even more fancy machines. I'll show you some concrete models of how to do that. We'll live at a fairly high abstract level of abstraction in this unit. But I think the core ideas shine through, and software frameworks are catching up to come to that high level. So we're getting closer to what programming looks like towards the end. But in case of doubt, I'll show you the cleaner algorithms as opposed to the more messy implementations as we still have them at the moment. The learning outcomes, therefore, are to know strategies to parallelize algorithmic solutions and problems, not so much implementing them in practice. I'll comment on the gaps there. You should also know when things are not possible to speed up by parallelism. I want you to know this concrete model that we'll look at, just to make these impossibility results formal. We need a machine model. We'll look at how to analyze things on this model, and then a few concrete examples of parallel methods. We'll see some fairly simple ones, and then the culmination of it at the end will be the sorting methods in parallel. And we'll start just looking at the models for today. What is parallel computation? I've asked you already what what your prior experience with that topic is. So I should maybe clarify on the content on the terminology there a bit. So what's listed here is concurrent programming. That's the model of having several things in a program be done independently and potentially at the same time, even though they might still be executed in sequence. One famous example is Python. It supports concurrent programming, but because of the global interpreter lock, for those of you who care about the technical details, it can't actually do real parallelism unless you have a C extension. So in a way, everything in Python is still sequential, but you can program concurrently. So concurrent means you program so that the program could be run in parallel. It's a programming model rather than an actual mode of execution. And yeah, you often have to do this still with fairly clumsy tools, explicitly calling threads, or if you have a better framework, then things get a bit more convenient. And so most people haven't done this, which doesn't matter much for this module. I'll show you the clean abstract world. And if you ever dive into, stick your toe into the practical side of things, the longer you wait, the better it gets. Things improve there a bit. Why do we want parallel computation in the first place? Well, it's simple. Money can't buy you everything, but it can buy you more computers. So if you can parallel your problem, even if it gets bigger, if it can be parallelized, you can solve it by putting enough money in. With some limitations, of course, but still. Often parallelization is the main route to scalability. There's two kinds of computers that are usually considered for parallel computation. And what we'll focus on is the shared memory parallel computer. So you should think of one big piece of memory, and it's all in one big box in a computer. but there's different CPUs that can work at the same time, and they can all talk to the memory independently, but they see the same memory. So the main way how they communicate is by putting certain values at specific places in main memory where they have a convention that this is used for communication. So we call these individual CPUs processing elements, just to be more generic, because they don't necessarily have to be full CPUs. This is for just to keep the terminology a bit more generic. But you can think of them as different CPUs working in parallel, all working on the same memory. You can have these in big servers. You can have hundreds of CPUs and maybe terabytes of main memory if you want to spend the money on it. So they can get fairly big, and even if the problem is fairly large, you can maybe solve it in a single box. And if that's possible, it's usually going to be orders of magnitudes faster than, well, the other big option you have is essentially a cluster of computers. There you would have individual boxes, each with their memory, and a CPU or several CPUs. And they talk to their own memory. So you need a secondary layer of communication, usually some network. It can be fairly fast, but most of the time these messages via the network are the bottleneck in the computation then. So for us, this is just to give you context. We'll not really talk about these. We'll mostly live in this scenario where you can solve problems really fast, and the main bottleneck is still the computation, not so much just communication. So here's our formal machine model for this, and it's based, lo and behold, on the model we already have, the RAM model from Unit 1. The main extension now is the RAM had this one, well, it should continue. The RAM had this one long piece of memory that actually is unbounded. And you had a single CPU that can do operations. Now you have several CPUs. The picture will look essentially the same as before. But each of these is a little random access machine. And they just share the same memory. So they each can access memory in the same way, the same operations, everything the same as before. But they're also numbered, so that's 0, 1, and 2. So they have an ID, and you can use this ID in programming them. Otherwise, they're like before. They also have a word size. That's a second parameter. And we have a third parameter next to input size and word size, which is P, the number of these processing elements, or the number of RAMs. Now, they each run a RAM-style program, the same kind of programs we've used before. And we'll allow ourselves, like before, we'll write pseudocode instead of actual primitive instructions. And we'll extend the pseudocode with instructions that can run in parallel. I'll show you examples on this next week. But I want to stress one important point. The assumption here is that all of those run in lockstep. Each of the, okay, my picture's gone. Well, let me draw it on this slide then. Each of these RAMs does one instruction in one time step, and then they all come together and wait for the next clock tick. So there's one clock for all of these RAMs. They have a synchronous timer. It's a feature of this model that makes programming easier. It's a feature that makes it less realistic, because most machines that we can build don't work exactly like this. They have separate clocks, and they can even run at different speeds. But that also means a lot more messy consequences. So we'll ignore that here. We'll design algorithms with this slight simplification, but you can translate much of it nevertheless if you don't rely on this feature too heavily. I'll comment on that again later when we look at specific examples. So in a way, it's the model we had before, but one long big memory that they all share, plus they run in lockstep. They all do one step, then they all write back their results to memory, then they do the next step, and so on. In particular, if they all access memory, they all happen to do this at the very same time. Because they access the same memory, we have to somehow say what happens if several people access the memory at the same time. And there's different conventions or different versions of this PRAM model. So P is the parallel random access machine. And then you have certain prefixes before that that tell you how memory accesses are handled. The most restrictive one says exclusive read, exclusive write. You, as a programmer, have to guarantee that in any time step for any input, only ever a single processing element is accessing each position in memory. And the assumption is, if that is ever violated, the machine just explodes and you're to blame. So that model is very strict. On the other hand, if an algorithm works for that model, it works for any of the others, and it will never cause problems. So if you can solve a problem like that with that constraint, that's great. This restriction is a bit overly strong. We don't really need that. The typical standard assumption is the CRU RAM, concurrent read and exclusive write. Because it doesn't matter so much if several people read the same memory cell, there's no inconsistency that can arise from that. But we still insist that any write access is from a single processing element only. And the last one, you can try to also give that up. You allow concurrent writes, but now we're in danger territory because we have to say what happens. We need a rule for resolving the write conflicts, and there's different further variations. One option could be, okay, it's fine if several people try to write to the same location, but if they do, they have to write the same value. And again, it's up to you, programmer. If you don't make sure that that happens, just the machine explodes and you're to blame. Or the program crashes or something like that. So it's up to you. But if you guarantee that, the hardware says, fine, nothing really happens. They all write the same value, so no inconsistencies. Or the machine could say, I allow this, but you have to deal with the consequences. You can do anything, but which value gets written to memory is unspecified, and your program has to be correct no matter which one wins. That's another option. Guess what actual hardware does? It's much closer to this one. And it gets worse because they can reorder statements, and it gets worse because things are not in lockstep. So many of the problems you're facing as a programmer when you're implementing things and try to do concurrent programming is dealing with the limitations that hardware was designed to be very fast and offload a lot of the responsibility on you. That said, we'll mostly look at these. So we'll assume that our programs have to make sure they don't concurrently write to the same place. That's a good way to program even those machines that allow arbitrary writes, because often it's really tricky to get those right. Let me show you this one, and then we'll finish for today. Every model of a machine has to tell you what is the cost of executing things. For the standard word RAM, it was simple. Just the number of steps was the total cost, the time. And maybe we were also looking at the total space. How many memory cells did you need? Now, time has become a little more tricky now because we have many processors. It's still not so hard because they run in lockstep, remember. So we can still define time as the number of time steps until all of the processing elements finish. And this is also called sometimes called the depth or the span. In particular, span is widely used. We'll come back to those terms. So that's the time of a PRAM program is the number of time steps until all the processing elements say they're done. By the way, we don't assume any limit on the number of processors. So it's not like, okay, my phone has 8 processors. Great, so that's all I can ever use. No, no, no. PRAM says you can have as many. It's like the RAM, like the memory in the RAM model. It's unbounded. You get as many as you wish for. And we'll come back to that assumption. There's a second cost measure, though, that now becomes relevant, which is the product of the number of processors and the time, basically, or the span. That's the total number of instructions across all the processing elements. If you want, you can think of this as something like an energy cost. Okay, it's great that you can fire up as many processors as you wish, but you still have to power them somehow. And we'll also tackle this assumption. So we have 3 things to look at now. And we'll try to minimize the time or the span, but we'll also have to keep work in check. Let me leave that here, and we'll pick that up next week. I'll go over some bits again, and we'll discuss about this really weird assumption that you have as many processors as you want. That's not very realistic, so we'll have to talk about that. There was one question I wanted to comment on, which is, I mean, we can, this is just as an aside, asynchronous functions, especially in Python, it's kind of orthogonal to it. It's usually useful to use those when you want concurrent programs or parallel programs. In principle, they're separate, but many things work better if you do them asynchronously. So there's a connection. Right. Good. Have a nice weekend. See you next week.